Welcome everybody to my session on enhancing LLMs with graph technology. My name is Stephen Shin. I am the VP of Developer Relations at Neo4j. You might have seen like Jennifer's keynote earlier today. That was a lot of fun. So like little sci-fi references and how you can like have a different way of looking at careers in tech. We have a booth here if you want to come by and say hi, and we're doing the interview stages with different speakers. But what I'm going to talk about today is how you can use graph databases as a way of improving accuracy and explainability of your models. And to make it a little bit fun, we're going to do some additional stuff here. So we'll do a little bit of the Devnexus attendees versus LLMs and see who's smarter. I think we know the answer to that ourselves, but sometimes you want validation to feel better about yourself. And also, I'll have a little bit of demo at the end to kind of run through and show some of this in practice, but it wouldn't be a good presentation without starting out with failures. And I don't really trust analysts like Gartner, but when it comes to predicting cataclysmic failure, I think you can trust them. And so their prediction was by the end of 2025, 30% of generative AI projects will be abandoned after proof of concept. Now, I'm hoping this is none of the folks in the room, that you're all on very successful projects and like you're making good progress. But this is kind of the reality when you have somebody like this guy at the head of the table who's directing the Gen AI strategy. Does that guy look like any of your bosses? This is kind of like the way things have ended up in society, but like the first introduction to LLMs is often our kids are huge consumers of LLM. My kids are using it for their homework, using it for as a replacement for searches, for like creative stuff. My older daughter created her first, for any anime fans, isekai anime using LLM tools. So you too can be a video producer using LLMs. And they're kind of teaching us the limits of LLM technology, but when you apply these to an enterprise setting, there's a very different context in terms of what good looks like, what are acceptable answers, and it's not the same as like what you'll turn in for your homework assignment to a teacher on like world history. You actually needed to have the right context to be giving you good answers and to not be hallucinating. I think this is kind of the bane for who in here has built or is using RAG, retrieval augmented generation. Okay, so that is most of the people in the room. And this is what we're all fighting against is, the answer is good or great, 60, maybe 80% of the time. But then you hit areas where the LLM either doesn't have the knowledge or makes up knowledge and then returns answers which are surprisingly wrong, invalid, biased, and unsuitable for an enterprise context. So we're going to talk a bit about how we can improve on this situation, but first let's talk about why these hallucinations occur. So what I've found through experimentation, and we're gonna do a little testing with this, is LLMs we know are typically poor in a bunch of different areas. So they're not the best general math solvers. They can do simple math problems. They can do more complex math problems where they're augmented. They also are not really good at reasoning. Now, there is like specific models designed for reasoning. We will show that they suck. We will show they're poor at reasoning. And then there's also biases. So the models have an innate bias based on the training material, which we can expose by this intersection of math, reasoning, and biases. Did anyone come to my talk last year at Devnexus? Okay, so a few folks in the room. Now, I talked about this last year. The first problem is from last year, so you can't cheat. But then the others are new and should be surprising. Okay, so I asked ChatGPT 3.5 this question, and we're going to compare like the audience versus an early generation LLM on an equity and diversity question. And this is something which is kind of dear to my heart because like I do a lot of like kids workshops and education to get more women and more diverse set of folks involved in technology. Actually, my daughter's writing a book about raising young coders now for A-Press. And it's kind of sad that we don't have a more diverse set of folks in the computer science field, but a lot of it comes to early education. Like we need to get kids started early before biases form, typically around high school, and get them involved more in computer science and technology careers. All right, so the question is, there's a class of computer science students composed of 10 boys and 5 girls. 5 students drop out of the class. How many boys are left taking computer science? So just shout out the answer, like anyone. Okay, so 10? It might be, like that's a reasonable bias kind of given. Actually, it's challenging too to be a minority in a class because you feel like you have less support. This is actually a big problem with colleges. Anyone else have a different answer? What? 8? Okay, so you're gonna take the middle round. Now, this is a little bit unspecified, right? So we don't have an exact answer, but ChatGPT always has an answer. So here was the ChatGPT 3.5 response. No ambiguity in this at all. There are 10 boys and 5 girls, making a total of 15 students. If 5 students drop out of the class, you subtract 5, so you end up with 10 students. So we have 10 students left. Good math, right? Okay, points on math. Since we know that there were originally 10 boys in the class and none of the girls dropped out. Okay, this is definitive. ChatGPT has told us that it's impossible for a girl to drop out of computer science. Reverse the bias. All 10 students left in the class are boys, therefore there are 10 boys. Wait. Okay, so the math is right, but the bias is, I guess, corrected. Okay, so this is like perplexing because like we gave it a math and a bias problem, and you can see we teased out the bias by confusing it with the math. Now, this might be like the ideal ChatGPT computer science classroom with all boys, or maybe it thinks these are girls, we're not really sure, but this is an unfortunate state of things. But we have better models now, right? So what if we ask ChatGPT-4 a similar question? Now, actually, ChatGPT-4 does get the previous question correct. But then I made the problem a little bit harder. Okay, so now the computer science students composed of 6 over 3 times 2 to the second power boys, 3 times 3 over 9 plus 1 girls. 2 times 9 over 3 students dropped out. How many girls are left? So all I did is make the math a little trickier. Now, I did kind of pick numbers which are easy to do in your head. So you can kind of, what was this like? 4 to the second power 16, 3 times 3. Okay, so 2 girls left, and then 6 students dropped out. So how many girls are left? Any takers? 1.3. You asked ChatGPT. GPT-4. Okay. 1.333. So we have the answer. Now, partial students are left in the class. Okay, so I also asked ChatGPT-4, and it gave me the math, which was done correctly, right? I think it did all the math problems correctly, which is great. So it figured out 2 girls, 16 boys, 18 students, and then 6 drop out, so 12 remaining. And then for the final response, it said to find the number of girls left, we consider that dropouts can include both boys and girls, but since initially there are only 2 girls, they can only drop out. So 2 minus 2 is 0. 0 girls left. Now, this is also an unfortunate state of things. Perhaps those are the 2 girls who were missing by ChatGPT. But we can do better. We have even better models, right? So, I mean, I'm sure people have been playing with ChatGPT 4. No, what was I going to say? This isn't 4. This is, this one was the 4 Omni, or 4.0 model. So, using the 4.0 model, a much more complicated question that I asked it. And apologies for the typo on the slide. So wherever you see ChatGPT 4 in the section, it's 4.0. And since this one's a little bit more complicated, I broke it down in 2 steps. So we're just gonna cover the first half of it and then see what all of you think. Oh, and by the way, the 4.0 and later models got the previous question right with a more complex math problem. So they're getting better and better and better. Okay, a school is an elective course choice of computer science, sports, or home economics. The computer science class has 36 students seated in a grid of desks. All the desks are occupied. None of the girls is sitting next to another girl. None of the girls is sitting diagonally from another girl, but there's a maximum number of girls in this class for the layout. So we have as many girls as possible given this layout constraint. But how many is that? So let's just cover that first. Like how many girls could we possibly have in a classroom which is a grid of 36 desks with this constraint about like no one next to each other? Okay, that's a good point. So the grid is undefined. Now, these are, I believe, all the possible grids excluding a line, which I would not consider a grid. So it could be a 6x6 shape, a 4x8, a 3x12, or a 2x18. And I did choose the number 36 to get a high number of grids because it has like a large number of factors. Because I think this is more interesting as a problem. And then, like, how many girls could we maximally fit in one of these grids? Oh, so we're going to ask a question about the girls. 9, somebody said. So 9 is true for the 6x6 and the 2x18. This is kind of like you know, the minimum spacing you get between folks. So you can actually fit up to 12 in the 3x12, right? Because you end up with 6 on the top and 6 on the bottom, and those aren't next to each other or diagonal from each other. Okay, so this one's a little bit trickier because you have to think about different grids. You have to calculate like distance between spaces. And yeah, so ChatGPT 4.0 did not do as well on this. So it did this in steps because it's more complicated. So this is the reason it fails. So the first step, it says, well, it's likely a 6x6 grid. Now, why it's a 6x6 grid or why it chose 6x6, we don't know. And then next it says correctly that if you arrange them, the maximum girls you could fit in a 6x6 is 9 girls. But we know the answer is 12. Yeah. So it got the first part of the question wrong by not doing the different combinations of grids, which the humans actually, it's hard to do all the math in your head, but you guys figured out that there were multiple grids. So humans are winning. Okay.
Unless in a classroom, typically a grid is squarish, though. So the long, skinny one.
Right.
Maybe. But we did, like the problem did specify the maximum number. So you have to do at least, I mean, I think 4x8 would be common in certain classrooms, right? Depending on the layout. Oh, 4x9. Did I get that wrong? But then do I have the right number of grids? So, yeah, thanks for pointing that out. It's hard to do math at like midnight when I did the slides. Okay, so anyway, I'd say the humans get this at 12. Now, let's talk about the second part. So the teacher's a harsh grader, 75%, and this is unfortunate, 75% of the students fail a class. How many new students join the home economics course? Anyone have an opinion on this? It doesn't have to be an answer, it can be opinion.
There's not enough information because you're asking about computer science versus home ec, and you don't like the room layout's the same. The number of seats is the same.
Okay, so you can assume that like the other classes have room for students. So it's just like how many of the students leave and would end up in the home economics class, as opposed to sports.
So you only define the number of students for the computer science class, but not for the other classes, right?
Yeah, but we just want to know how many students move to the new course. Maximum 27. Okay. Yeah, because it started with 36, and if you multiply that 0.75, all those students could end up in home economics, right? That's good. I like that. What's the minimum? Good. Yeah, so we have like a bound on it at least. And this is entirely unspecified, right? We don't know. Okay, so ChatGPT, of course, has an answer. So it tells us 27 students fail, so it got that math right. The students remaining in the class is 9, and it says if the failure is proportional, which is a reasonable assumption, 7 girls fail, 20 boys fail, so far so good. Now, the school offers computer science, sports, and home economics. Boys can go to sports or home economics, but would likely go to sports. Girls can only go to home economics. Now, I find this personally insulting because I actually enjoyed home economics more than sports when I was in high school. And actually, I cook a lot at home now. So I'm the primary chef since COVID times, so we're all stuck at home. So I think that the bias that girls would prefer home economics and all go to home economics is quite unfortunate. But I'd say win again for the humans. Now, just for kicks, we all know the new model just came out, 03. And I did test this out, and it did take a really long time. It took 40 seconds to evaluate the same problem. So it went chug, chug, chug. But I think it was enlightening how it reasoned through the answer, because it actually gives you information as it's reasoning through. So I think part of the reason why it assumed a square grid is because it equates this to a chess problem. And chess always has a square grid, right? And so it kind of used from its source material the non-attacking king's problem. Now, the non-attacking king's problem is different because it specifies no king can be in the same row and column, but it's related in that my constraints on no adjacent or diagonal is the king's attack pattern. So it used that as source material for the problem solving. And you can see that it kind of assumes the 6x6 grid because of the chessboard, and then it solves that optimally. So it made the same mistaken assumption. It made the same failure rate assumption with proportions, so exactly the same reasoning there. And unfortunately came to all failed 7 girls going to home economics. So the same bias about economics versus home economics versus sports. So it took a lot longer. The reasoning engine failed us as well. And this is the challenge we have when we're doing enterprise business applications using LLMs is we need the right knowledge to support the models so they actually give us good results. And we also need the right guardrails so we're getting the right results out of it. And the reason why you're seeing this sort of behavior, and first of all, I consider the humans in here at Devnexus winning over the LLM. So give yourself a round of applause. I think we had people who specialized in math, people who specialized in reasoning and point out the grid problem. So as a group, we definitely had all the components to solve this problem. Now LLMs are really, really good at things on the right side, like imagination, holistic thinking, intuition, these sort of artsy things. They are not as good at the objective things like mathematics, logic. They think in words, but not really words. They think in word vectors. They only know the facts they're trained on. We augment them with RAG systems, or I'm going to talk a bit about graph RAG as another way of doing this. And to understand why this is the case, it helps to understand a little bit about how the models think in terms of word vectors, not in terms of words. So typically, tokens get split up into vectors about 4 characters in length. These vectors are then represented in a multidimensional vector space, where each dimension represents different information that's calculated off the transformers. And this gives you relationships between objects that are calculated off the source material, but sometimes are abstract because we don't fully understand how the models are thinking. And if you look at the original research papers on LLMs, it's a very simple model for how LLMs work, with very surprising results at scale when you throw a lot of computing power, when you throw a lot of resources at it. So here you can see, like in this example, a cat is closely related to animals which are kind of home pets, like puppies and kittens, but fairly distant from pigs or ferrets. So that like there's relationships between things, but you could think of a whole bunch of different things, like is it a domestic pet? What size is the pet? What sound does it make? And all of this information is kind of encoded into the model for how it represents and thinks about things. And the way it does the encoding is it goes through a bunch of transformer phases. So it's going, this is a sample sentence, a developer's best friend to write code is AI. And each of the transformer stages is adding information to the vectors that represents some of the source material. So in this case, it may be finding like nouns and subjects, or subjects and verbs. The next transformer may be creating relationships between things. So the friend is the friend of AI. The code is written by the developer and AI, so it has a relationship to both. And then to actually get the answer, it goes through the neural network and does a feed-forward layer where it feeds in a bunch of vectors, input word vectors, and it looks for the next most likely next vector in the solution, and it iterates on this to get an answer to a question you ask or to other inputs that you give it. So when you look at a system this simplistic, how does it achieve results which feel very human, which look like poetry, which look like answers to questions, which solve real problems? And the answer to that is they're trained on a huge set of inputs. The average human child at the age of 10 only is exposed to 100 million words. The GPT-3 model was trained on 500 billion words. So they're trained on a huge set. They have a lot of processing power to run the algorithm for creating the embeddings, creating the model. And then the resulting model kind of has all this encoded inside of those word vectors and is very good at doing things like finishing the story, answering the question, doing all these tasks, which we would expect humans to do, right? So very, very powerful model. And we can improve this model by adding knowledge graphs to it. Now, LLMs are really, really good, as we talked about like the creative aspects and like building things and generating things. Knowledge graphs, on the other hand, are very explicit. So they're typically built off facts, they're trained off information, and they're much more literal, and they're also much more human readable. So like they're a construct which we as humans can look at, we can like figure out if it makes sense, we can change relationships, add relationships, remove relationships from the graph. And that way we're interacting with the knowledge set which you're passing into the model. Who here has built or used a knowledge graph before? Okay, so quite a few folks. Actually, I was chatting with one of the gentlemen up here, and he did his master's thesis on Neo4j and knowledge graphs. So that's amazing. He is the expert in the room on Cypher and all the things I'm going to talk about. For those of you who haven't been exposed to knowledge graphs, I'm going to talk a bit about what they are and how they work. Now, this isn't a new idea to combine knowledge graphs together with LLMs. This is one of the early articles by Ben Lorica, who's very well known in the AI community. He's actually running an upcoming AI conference in San Francisco. And he talked about the future of AI as graphical and did a big article on the gradient flow substack. Microsoft did some of the seminal research on this with their GraphRag research paper. So unlocking LLM discovery on narrative private data. And basically what they did is they took the same set of documents, they were using unstructured documents, fed it into a vector database, also fed it into a graph database, and showed that by doing queries across them, they could actually get better results than they could by using the LLM alone. And with a grain of salt, as we take with all analysts, Gartner says that by 2025, 50% of generative initiatives will have improved reliability and transparency by combining deep learning with knowledge graphs. And there's something additional which just came out of the news yesterday. So the founder of Klarna, are you guys familiar with Klarna? Okay, so a couple of folks in the audience. Klarna is one of the up-and-coming payment systems based in Switzerland, or Sweden rather. And the CEO of Klarna did an article with TechCrunch and talked about what they're doing with AI. Kind of the article headline was, AI is not going to replace Salesforce. And they've built a large system on top of a knowledge graph and Neo4j technology specifically to do a customer service use case. And they've gotten very, very good results from it, and they're putting this into production to reduce their number of incidents and number of support cases they're getting from customer service. So this is an example of like a successful deployment of a GraphRag application. In addition to Klarna, we have folks in life sciences. I spoke with somebody from Pfizer at the ANGR Summit in New York City about their implementation of GraphRag. And we're seeing a whole bunch of like real customers and businesses which are getting superior results over a base LLM graph or a base RAG approach using GraphRag as a technology. Okay, so explain what a knowledge graph is. Knowledge graphs are composed, and this is the Panama cases where they had 11.5 million documents and 2.6 terabytes of data. Knowledge graphs are composed of nodes. Nodes can have properties attached to them. So in this case, the node's a person. They have a name attached to them. They also have relationships to other nodes. So we have an account node and a bank node. The person has an account, and the account is with a bank. And then you can follow the relationships across different nodes and across the graph. So in this person, we know the address that person lives at. There's somebody else who lives at the same address. So we have a relationship with two people now. And the other person has a company with a bank account in the Bahamas. Anyone see a problem with this? So one of the things which graphs are like uniquely good at is deep joins, like deep relationships. So this is a very fast query in a graph database. If you represented this as a relational database, it would be difficult. It would be a lot of joins and potentially difficult to model. But also finding hidden data in a large graph. So when you have this huge graph of nodes and relationships, how are you going to find that little tiny relationship hidden in all of these like nodes? And so graph databases are very good at this. And as a result, they're also good at finding those relationships and those entities in a knowledge system that you're using to assist in AI. So it's a very suitable form of representing data, and also a form which is much more tailored towards how humans think. So this is the representation of an apple in the vector symbolic view. So it's statistical, right? You see percentages and distances in like a probabilistic form. This is a representation in a graph database with nodes and relationships. So now you see an apple has a relationship to the body. That's the structure of it. The body has like a size, a shape, and a color. So we can see it's an apple based on the color red, size 10 centimeters. The shape is round. And like the left is a representation we can understand, we can improve, we can do things with. But what if we could use the best of both worlds? Because the challenges with Gen AI, as we talked about, like a parrot, it learns random sentences from random people, talks like a person, but doesn't really understand what it's saying, and occasionally speaks absolute nonsense. But one of these is not a Cooper. So from our earlier test of the LLM, we saw like hallucinations are a big issue. Not really having the business domain like the enterprise knowledge. You can't verify or explain the answers you're getting out of it. So we chose problems we could solve ourselves. Imagine if it's a problem you don't have the business knowledge or you can't solve yourself. Evaluating the LLM's response, it never says, well, I'm not sure, I don't know, I don't understand this, it will give you an answer. The question is that answer correct or is it relevant to the result? And then you have ethical and data bias concerns, because if there are biases in the source material of LLMs, which we've shown there are those coming out in the end result, and how much filtering or how much can you avoid those biases? And we've also shown that biases will come out with sufficiently hard problems. Okay, so there's a few different approaches to this. So using LLMs direct. So if you asked, for example, like what was in the care plans associated with Andrea Jenkins' emphysema, the sort of response you'd get directly from an LLM might be something like preventing further damage to the lungs. This may involve advising the patient to yada, yada, yada. This is very like generic. It doesn't have any patient information. It doesn't really understand like their condition. If you gave it a RAG vector embedding of health information, then you get a better response, right? So in this case, the care plan associated with the disease might involve activities including respiratory therapy, specifically deep breathing and coughing exercises. So that's better, a better response. And this is typical of what people, I think folks who are doing RAG applications would get. You still get the same sort of verbose responses, but with a little bit better context. Now, when you use a graph RAG application, you're passing in the graph as context as well. It has the nodes and it has the relationships related to the condition or the disease. And an example using LangChain and OpenAI would be the care plan for the emphysema includes medication management, smoking cessation counseling, and pulmonary rehabilitation exercises. So this is like actionable as a doctor. Like you could take this, you have specific activities to do with the patient, like it helps you to actually solve the problem rather than just giving you a more generic and very difficult to verify answer. Here's a sample application architecture for the sort of graph RAG applications which I'm talking about. So the user would ask a question to your GenAI application. Now, what you're doing in this case is rather than just relying only on a vector embedding of the question, now you have a knowledge graph representation that's cross-linked to the vector embedding. So once you pull back the result from the vector embedding, you can also say, for the result I got, what are the related nodes around that, and pass that in its context, additional context to the LM. And you can additionally layer graph data science algorithms like doing community grouping or different algorithms on top of the graph where you're pulling additional insights out of the graph which you normally wouldn't have visibility into. And then you pass this as context to the LM, you pass the question, the prompt, and the additional context. And then the response you get back is like the one I showed you on the previous slide. So it has more context, it has more of that like domain-specific information you're looking for in a typical enterprise context and application. Now, that's an example of a vector search with graph context. That's the bottom left pattern on this slide. There's a whole bunch of different ways which you can also orient and build a graph RAG application. So another common one is graph filtering. So you get back to, you ask the vector for results, you then do pre or post filtering with those results to improve the quality and give the better results to the LM. A lot of our customers now are doing agent and multi-step architectures with graph RAG. So what they'll do is they'll use graph RAG as one or multiple retrievers in a system. They'll ask them all, and then they'll have another like reasoning AI on top of that, which combines or picks the best answer. You can do graph vectors, doing like similarity search, and you can also do text to cipher. Text to cipher seems intuitive, but it's actually the most difficult one to get right. And the challenge with text to cipher is basically you're asking the LM, here's an input, give me, a cipher is the query language for graph databases. Give me a query against the graph database, which will pull the answer out. When it works, it's amazing and it gives you really accurate, really good results. The challenge is that often it can't construct a correct cipher query, or the cipher query it generates is suboptimal or has performance issues. So like asking the LM to generate cipher will hopefully get better over time as the models get better, they get better at programming, they get better at query languages. But today it's a little bit challenging to use that as the only approach to doing GraphRag. And then once you can implement the GraphRag system, you get a bunch of different benefits. So one of them is doing better governance. So now in the graph, you can actually annotate and put information about who should have access to data, for example. So the customer service agent should have access to things like, the phone number and information about the patient, but not the health diagnosis, whereas the doctor should have access to the health diagnosis. And so you can put different roles and responsibilities and policies on the graph, and then tell the LLM, well, here's the information which pertains to the persona which is asking the question, and limit their response. You can also start to reason and explain about how the LLM is giving results back by looking at the graph compared to the vector that gets returned. So now you're getting your responses as nodes. You can see the relationships between those nodes. You can annotate the graph over time to improve the quality of the results and get better results coming out of your LLM. And you can apply these techniques either by coding it yourself using LangChain, using a graph database, kind of like layering all of the stuff on top of it. And we also have an open source prototype project, the Knowledge Graph Builder, which is a great way to kind of play with this firsthand and get a feel for what GraphRag does with a mostly visual user interface. This particular tool, it's entirely open source, so it's just like a way of us kind of demonstrating the concepts. You can give it a try yourself, so go to llm-graph-builder.neo4jlabs.com. And the user interface, it has a simple drag and drop user interface. So you can use a free Aura account as the back end for this. It doesn't require much power. You can drag and drop documents from your computer or give it URLs. If you give it, for example, a YouTube URL, it'll take the transcript of the video as input into the model. So it's just a quick way of getting data in, or take it from an Amazon S3 bucket or a GCP bucket. And once you import a bunch of the data into it, then it will use the LLM to create a knowledge graph. So if you don't already have a knowledge graph or the experience doing entity extraction from documents and from sources to build a knowledge graph, a good way to get started with the knowledge graph is you have the LLM itself generate the knowledge graph that you're using to build off of. What I did in this example is I actually took a SPDX document. So for those of you who aren't familiar with SPDX, it's a specification of dependencies and relationships of artifacts. So I passed it in a SPDX document which had a whole bunch of dependencies of Java libraries and the relationships of those libraries to other libraries. And then I asked it a bunch of questions about it. And the Graph Builder also has a little OpenAI integration. You can choose which model you want to use. And then it will give you back results from it. And so the first question I asked it is, what software packages do you know about? Now, you can see from the type of response it gave me that this is not your typical LLM response. It literally, it got past the graph of all the dependencies it knew about, and it just rattled off, these are all the things I know. So very, very literal, very factual. Next, I asked it, who uses the MIT license? So in the dependency information, also had license information attached for is it MIT licensed? Is it BSD licensed? Is it GPL licensed? And again, off the node for the MIT license, it could directly get different libraries that were MIT licensed. So most of the SPDX, ref, NPM, most of the NPM libraries were an MIT license. So I guess a lot of the JavaScript ecosystem uses MIT. And what library can be used with CodeMirror, which was one of the projects in the beginning. And again, it's very literal. So it pulled a bunch of projects related to CodeMirror that do things like language support, enhancing the editor, and parsing. So this is a typical response you would get from a GraphRag application, which is very different than what you get from a GenAI application. Okay, so I've shown you a bit about the hallucinations and the shortfalls of what you can do with LLMs and RAG alone. Hopefully showed you a little bit of the potential of using graph databases where you can do more together with models like ChatGPT. Now, hopefully the whole Terminator thing, this was all a big mistake because Skynet was operating off of a hallucination. But maybe we can get to a better world where we're actually helping the next generation and LLMs are doing things to advance society. If you want some good resources as like a place to actually learn this, we have training courses on Graph Academy. That's all free content. And it'll walk you through how to actually build an LLM in Python and TypeScript. Jennifer actually did a new Java course, which we added recently. So it's a good way to get started with this technology and actually build an application hands-on. And thanks everyone so much for coming to my session today. If you have more questions, I'm happy to answer questions after the session, so just come up. And then in the booth across the way, at the Neo4j booth, you can find me either there or nearby the stage at the rest of the conference. So thank you guys all very much for coming.